All right, so today we're going to be covering a very important topic. It's called the systems of equations. And this systems of equations that we're focusing on today, you should have been exposed to this in Algebra 1. So we're going to go ahead and go back to these ideas that you all have seen with systems of equations. And then hopefully by next week, we'll be able to use these ideas of systems of equations to help us solve more complicated systems of equations. So for today, I really just wanted to go ahead and go over the main ideas of systems of equations and really how to be able to solve them. So whenever we're dealing with systems of equations, all that really means is we're dealing with two or more linear equations. Okay, so once again, systems of equations really just means we're dealing with two or more linear equations. So whenever we're dealing with two or more linear equations, a very important feature that we want to look at is where these two equations that you're given, where they intersect, if at all. So in this systems of equations unit, we really just want to focus on the different types of solutions that you have. So whenever we're dealing with two linear equations and we have them graphed on a coordinate plane, a situation where you only have one solution would be this. So once again, these are just random lines. So let's just say you have that line and then another line coming down. Our focus for today is really just focusing on this intersection point between these two lines. So notice here that these two lines have only one intersection point. So this one intersection point means we only have one solution. And then in the other case, we have a situation where it is no solution. So it would look like this graphically. So let's just say you have a line like this, and then some other line like this. Notice that these two lines do not intersect with each other at all. So because there is no intersection with these two lines, this would be an example of a no solution case. And one important thing that you want to note here is that whenever you have no solution, that's really whenever you're dealing with parallel lines. Okay, so make sure to write that down. That is very important. So that's an example of a no solution. Let's look at an example of an infinite solution case. So an infinite solution case would be this. Let's just say you have a line. Let's just say you have a line that looks like this. But what if you had another equation that had the same exact line as shown here? So let's just say we draw the other line, but it's exactly the same as the one in blue. So in this case, notice that these two lines are really intersecting at every single point. So in this case, we would have an infinite amount of solutions. And one important thing that I really want you to write down here is whenever you have an infinite solution case, that's whenever we're dealing with what we call coincident lines. And all that really means is we're dealing with the same line. So these two equations that they give you for an infinite solution case are exactly the same. Okay, so these are the main key features of solving systems of equations. Once again, you have a one solution case, a no solution case, and an infinite solution case. So for today, I just wanted to walk you through a couple of examples, going over the main parts of this worksheet. So notice here for this first part, they want you to solve the system of equations by graphing. So we'll look at that right now. And in the back of this worksheet, they want you to solve the systems of equations by substitution. So let's look at how to solve system of equations by graphing. So this is the first method of solving systems of equations. First method is always try to graph. If you're given a coordinate plane, so in this problem, in number 1, they give you two separate linear equations. Each of these equations has its own slope and its own y-intercept. So on the graph here, we want to go ahead and graph these two linear equations on here. So let's go ahead and graph this first one on this coordinate plane. Notice that that first one has a y-intercept of -6. So we're about right here. And the slope, be real careful with this. The slope for this is -5/3. And once again, there are different ways to interpret this. But what I would like to do for this one is say that, our slope is equal to -5/3. So what I did here is I put the negative on the top. And please remember that whenever you're dealing with slope, that is the ratio of the rise over the run. So if we look back at this graph, if we start off with a y-intercept of -6, we're going to have to go down 5 and then 3 to the right. The only problem with this coordinate plane is that it doesn't extend further down. So what you can also go ahead and do is do the opposite of what we just did. So instead of going 5 down and 3 to the right, we can go 5 up and 3 to the left. 1, 2, 3. So we're about right here in order to backtrack the point. Okay, and we do the same thing. 1, 2, 3, 4, 5. 1, 2, 3. We're about right here. Same thing. 1, 2, 3, 4, 5. 1, 2, 3. Okay. And then what we would do is just connect the lines as best as we can. Okay. So that's how the line should look for the first equation. Now let's go ahead and graph this other one. So we start off with a y-intercept of 5. We go up 1 and 6 to the right. Okay. And if you wanted to backtrack from this point, we would go down 1 and 6 to the left. 1, 2, 3, 4, 5, 6. And there you go. Your intersection point would actually be right there. So this right here, this line is the graph of this equation. And notice that they both meet. These two equations, they both intersect at that point. And we want to figure out what that point is graphically. And you'll notice that if you look at this graph, the intersection point is negative 6, comma 4. And this intersection point would be your final answer. So notice in this example, we only had one solution. And that is very important. Okay. So let's go ahead and go over to example number 2. In example number 2, they give you, once again, two different equations. Let's go ahead and focus on this top one, y equals 5. Please recall that whenever you're given y equals 5, or y equals some constant, in order to graph that on the coordinate plane, this will be representing a horizontal line. So y equals 5 would look something like this. You have a horizontal line right here. And let's go ahead and graph the other line. We have a y-intercept of 7. Another way to rewrite this, not rewrite it, sorry, but if you focus on the slope here, the slope is 2, which is the same thing as 2 over 1. So if we're thinking about rise over run, our rise would be 2 and our run would be 1. So that, I think, is a very helpful way of thinking about this equation whenever you're graphing it on the coordinate plane. So from here, from a y-intercept of 7, I go up 2, and then 1 to the right. And if you wanted to backtrack, you go down 2, 1 to the left, down 2, 1 to the left, down 2, 1 to the left, and you can keep on going. But notice here that there is immediately an intersection point. And that intersection point would be, based on this graph, negative 1, comma 5. So this would be your final answer for example number 2. And once again here, you only have one solution. Okay. So that's example number 1 and 2. Let's go ahead and go over example number 3. So in example number 3, same idea. The only issue here is that they give you these equations in some sort of a standard form. So the only difficult part here is being able to solve for y in each of these cases. And once you have done that, you would just graph them on here. So let's look at this first equation that they give us. 6x minus 5y equals negative 45. For these, I highly recommend you solve for y. So let's go ahead and do that. In order to solve for y, you move the 6x over to the right-hand side. You get negative 5y equals negative 6x minus 45. Divide by negative 5 on both sides. You get that y equals positive 6 over 5x plus 9. So let's go ahead and graph this equation on the coordinate axis. So you have a y-intercept of 9. We go up 6 and 5 to the right, but here we come across another issue. There is no space here, so we're going to have to backtrack. So instead of going up 6 and 5 to the right, we're going to go down 6 and 5 to the left. See right here? So down 6 and 5 to the left. Okay. So we can connect those lines as best as we can. Sorry. All right. And then let's go ahead and look at the other equation they give us. 2x plus 2y equals -4. Solve for y once again. Move the 2x over to the right-hand side. You get 2y equals -2x minus 4. Divide by 2. And you'll get that y equals -x minus 2. And once again, this negative is coming from the -2 divided by 2. So if we wanted to graph this on the coordinate axis, we have a y-intercept of -2. All right. And for this slope, for this line, the slope is -1, which is the same thing as -1 over 1. So when we're thinking about graphing it, we go down 1, 1 to the right, down 1, 1 to the right. And if you backtracked it, this is what would happen. You would meet at that point right there. Once again, graph it as best as you can. And you'll see that the intersection point right here would be -5, 3. -5, 3. And that would be your solution. Once again, here in this case, we got one solution. Okay. So hopefully that was helpful. For example number 3, once again, the hardest part of these is to be able to solve for y, which is what we did here in this whole process. After you solve for y, you can then go ahead and graph it and see if they intersect or not. So notice in example 1 through 3, we only had one intersection point, which gave us only one solution. So let's go ahead and look at example number 4. This one is a bit different case. So for this one, what I recommend is solving for y for that top equation that they give you. You get 6y equals -3x minus 12. When you move the -3x over, divide by 6 on both sides. You get that y equals -1/2 x minus 2. So notice here, one thing I want you to notice is that the slope for this first equation that they give us has a slope of -1 over 2, -1/2, and the slope for the second equation they give you also has a slope of -1/2. So here, these two lines share the same slope, but the only difference is they don't share the same y-intercept. So that's something to keep in mind when you're graphing these. So if you were to graph these on the coordinate plane, it would look something like this. So for that first one, we would start off with a y-intercept of -2. Go down 1 to the right, 2 to the right, down 1, 2 to the right, down 1, 2 to the right. You follow that same pattern. Okay, so that's how that first line would look, which is this one right here. So that one is that one. And then this one, let's look at this one. That has a y-intercept of -5. Same slope. Down 1, 2 to the right, to the right, to the right. Same idea. But notice here for these, they share the same slope but different y-intercept. And in this case, there is no intersection. There's no intersection present. So because there's no intersection present, we would say that this systems of equations would not have any solution. So no solution. And remember, the fancy symbol for no solution was the empty set. Okay. So either or is accepted. You can either say no solution or the empty set. All right, so hopefully that makes sense. For example number 5, I wanted you to go ahead and try that out on your own. Please make sure that this example is completed. Whenever I complete the binder check at the end of the cycle, I am definitely gonna make sure to look and see that all of these problems from the in-class worksheet are also completed. So please make sure you try this one out on your own and complete it. And I'm already giving you the answer for this one. This should be the answer, but make sure to show your work and graph it and confirm that that is the answer. All right. And for this last one, I wanted to go over example number 6, which is very important. So for example number 6, for that first equation they give us, what I recommend is you can either divide the whole thing by a -1 or multiply the whole equation by a -1. And the reason for that is we want to make sure we get rid of that negative sign in front of the y. So let's go ahead and divide by -1. If we do that, we do the same on the other side. So you get that y equals positive x plus 6. All right, and if we wanted to graph that on the coordinate axis, we get y-intercept of 6, up 1, 1 to the right, up 1, 1 to the right, up 1, 1 to the right. And if we wanted to backtrack, same thing. Okay. So that's how that line should look. And then for that other line they give us, notice here that they put the y on the right-hand side. If you really wanted to, what I think it would be really helpful is just to reorient this equation to have this on the left side and this on the right side. So if you really wanted to, once again, this is just reorienting. You're not really changing anything. So if you really wanted to, you can say that 3y equals 3x plus 18. And then now we have y on the left-hand side. We divide by 3. So you get that y equals x plus 6. Notice that these two equations, the first equation and the one we just found out, are exactly the same. So if you wanted to graph this one that we just looked, it would actually just lay on top of the red curve as well. Okay, and once again, in this case, these two lines would be what we call coincident lines. Make sure to write that down. Coincident lines. So therefore, if we go back to the top of our notes, whenever we have coincident lines, this is the case where we have an infinite amount of solutions. And please remember the fancy symbol for infinite solutions was the all real numbers. And once again, in this case, either or is accepted. So hopefully that was helpful. Let's go ahead and go over the next section of solving systems of equations. So just to recap really quick, this page was all about graphing each of the two equations they give you and graphically seeing if there are any intersection points. So in this first one, we looked at a variety of different graphs. We saw cases where we only had one solution, no solution, and an infinite amount of solutions. So for this next part, what if you weren't given a graph? What if you didn't have the ability to graph it? In these cases, there is another method that we can use. and that is what we call the substitution method. So the substitution method is really just another method to help us solve systems of equations. Specifically, it helps us solve systems of equations algebraically. So in this first part, we looked at solving systems graphically, but we can also solve systems algebraically with this substitution method. And you should have already been exposed to this substitution method back in Algebra 1. But once again, we need to revisit these concepts because they're going to be very important for our future study. So the idea here, if we look at the examples they give us, the steps that they give us, 1 through 4, remember, in these cases, we're focusing on two different linear equations, or two linear equations. They don't have to be different, but two linear equations. And the first step tells us to solve one equation for x or y and isolate the variable. Number 2 tells us to substitute the resulting equation from step 1 into the other equation for that variable. Number 3, solve for the remaining variable. And number 4, substitute your answer from step 3 into the original equation to find the other variable. Into either original equation. Okay, so let's go ahead and see what this means algebraically. So let's look at example number 7. In example number 7, they don't give us a graph, but they do tell us that they want us to solve the systems of equations by substitution. So let's go ahead and do that. Notice here, number 7 isn't the most difficult one out of all of these. So for this one, they actually already give us what y is equal to. And please remember that in step 1 of this process, they want you to solve one of these equations for either x or y and isolate it. So here, they actually already give us the isolated equations for y. So that is very helpful for us. Since they're already isolated, we can go ahead and try the substitution method directly. So once again, there are different ways you can approach this. What I recommend is this. Since they already give us what y is equal to, we can get this second equation and we can substitute in what y is equal to right here into this first equation. So that would look something like this. You would get that x minus 9 is equal to negative 7x minus 1. That's if you substitute this y equals into that y equals. Keep in mind y equals x minus 9 for that second equation, so that's why we have x minus 9 on the left here. And then from here, according to the steps that they give us, you would just go ahead and solve for x. So from here, what we could do is add 7x. You can also add the 9 at the same time. So you would have 8x equals 8 divided by 8 divided by 8. You get that x equals 1. But keep in mind, this isn't our solution. This is just one part of our coordinate point. So what we have to do in this case, when we already solve for x, is go back to the two different equations they give us, and you can plug it in to either equation according to the steps they give us. So here, it doesn't really matter which one you choose. You can either choose that one or this one. For right now, let's go ahead and plug this x equals 1 into this equation because it's just a little bit easier. So we're going to plug in x equals 1 into this equation. So you get that y is equal to 1 minus 9. Therefore, y equals -8. Once again, if you were to substitute in this x value into the other one, you should get the same y value. So your final answer for this question, for this example, would be 1, -8. So this would be your final answer. And notice here that you only have one solution. Okay. Let's go over to number 8. So in number 8, they give you two separate linear equations. One of them already isolates the y for you, but the other one is a little bit more difficult to work with. So if they already give you what one of the variables is equal to, then we can take advantage of that and plug in. We can substitute this right here, which is equal to y, into this other equation that they give us. So that would look something like this. You get 7x plus 3 times, make sure that this is put in parentheses, because remember, whenever you make a substitution, you should always include that parentheses. So you get negative 5x plus 30 equals 42. We simplify the whole expression. Don't forget to distribute. We can combine like terms. Subtract the 90 from both sides at the same time. So this -8x is coming from these two, 7x minus 15x. And then we're subtracting the 90. And you should get on the right-hand side -48. Divide by -8. You should get that x is equal to +6. All right. So x equals 6 here. Once again, this isn't our final answer. Once we have a variable that we solve for, you want to make sure that you plug in this x value into one of these equations. It really doesn't matter which one you plug it in. Let's just plug it into the first equation they give us. Plug in x equals 6. We get y equals -5x plus 30. Plug in the 6. -5 times 6 plus 30. You get that y equals -30 plus 30, which means that y equals 0. So your final answer will be the coordinate point 6, 0. And once again, here we have one solution. All right. Hopefully that makes sense. Let's go over to example number 9. So in example number 9, these are actually the more complicated ones, because in example number 9, if you compare that to the previous two examples, they don't isolate one of the variables for you. So in this case, you have to do it for yourself. So what I recommend is try to see if you can look at each of these two equations and see if there's an easier one to work with. You'll notice that for the second one, that actually is a little bit easier to work with, because notice that this y doesn't have a number attached to it, or it doesn't even have a negative attached to it. So that is actually very helpful to know, because all you would have to do is, for this one, I'm going to rewrite it. We would subtract the 7x. You get that y equals -7x plus 22. Now that we know what y is equal to, we can substitute in this y into the first equation they give us. So that would look something like this. 6x minus 5 times y. We solve for y, which is negative 7x plus 22. So let's make that substitution. Equals negative 28. You get that 6x plus 35x. Negative 5 times 22 should be negative 110 equals negative 28. Combine like terms right here. You get that 41x equals, and then add the 110 on both sides, equals 82. Divide by 41, divide by 41. You get the x equals 2. Now that we solve for a value of x, we can substitute in this value of x into any of these equations. Let's plug in this value of x into the second equation, just because. Once again, there's no reason why we're choosing one over the other. You can choose either or. Let's just choose the second equation that they give us. So plug in x equals 2. You get that 7 times 2 plus y equals 22 if we're using the second equation. You'll get that 14 plus y equals 22. Subtract 14 on both sides. You'll get that y is equal to positive 8. So therefore, your solution would be 2, 8. And there you go. That would be your one solution. Okay. So for example number 10, I want you to go ahead and try this one out. Once again, I gave you the answer already. Please make sure to confirm that this is the answer to that. Make sure to show all your work. Example number 10 is really similar to example number 9. So try that one out. And let's go ahead and move on to example number 11. One thing I want to point out though, for example number 10, before we move on, one little thing I want to point out is, remember, you don't always have to solve for y in these cases. You can also solve for x. So just to give you a little bit of a hint here, if you look at this first equation, I'm going to rewrite up here. Instead of solving for y, which would be a little bit more complicated in this situation, but doable, you can also solve for x. So here you would just add the 7y on both sides. You get that x is equal to 7y plus 53 for this first equation. So x equals 7y plus 53. And then what you could do is substitute in this value, this equation for x equals into the second equation in for x. So that would look something like this. Negative 4 times 7y plus 53 minus 5y equals 19. And notice here that you're going to not solve for x, but you're actually going to solve for y in this case. So keep that in mind when you're doing example 10. Example 10, here you're solving for y, and then you're going to use that y value that you ultimately get from this and plug it in and substitute it in to any of these two equations in order to find the x value. So try that one out on your own. Once again, the answer is already here. Try your best to confirm that. And let's go over the last two examples for today. So example number 11. If we look at these two equations, this top one would actually be easier to work with. So what we could do is divide everything by 2. And you'll get that y is equal to 3x plus 5. Now we have solve for y. We can substitute in this y into the second equation for y. So you get that 3x. Be real careful here, minus, you're making a substitution, put a parentheses, 3x plus 5 equals 5. Make sure to distribute the negative into each one. You get 3x minus 5 equals 5. Notice that the 3x and the 3x will cancel out, and you're left with negative 5 equals 5. And here, this is kind of going back to the ideas we talked about when we were dealing with absolute value equations. Here, in this case, you have to ask yourself, is this statement a true statement? Is it a true statement or a false statement? And you'll see that this statement right here would be a false statement because negative 5 does not equal positive 5. Okay. Negative 5 does not equal positive 5. So therefore, for the systems of equations, we would have no solutions. And another way to write that using a symbol is the empty set sign. So in this case, we have no solution. Okay. So hopefully that was helpful for example number 11. And example number 12. Let's go ahead and go over that one. This one, I believe, deals with a good amount of fractions, so I just wanted to go ahead and go over this one with you all. And this is the final example in this video that I wanted to go ahead and talk about. After this, I will definitely tell you what's going to be for homework, okay? So for this one, notice that they give you two complicated equations. Here, honestly, it's up to you to decide which one you want to use, which one you want to solve for. So what we could do is work with the second equation. Once again, it doesn't really matter which one you work with, but let's just say you chose the second equation. So I'm going to rewrite this over here. Okay. And what we're going to go ahead and do is solve for y. Let's try that out. So you subtract the 4x, negative 3y equals negative 4x minus 5. Divide by negative 3 on both sides. You get that y is equal to positive 4 over 3x plus 5 over 3. Okay. So now we're dealing with fractions, which is a little bit more complicated, but just be real careful with this one. So now that we solve for y in the second equation, we can use this and make a substitution for y into the first equation. So let's go ahead and do that. So you get that 5x plus 7 times, make the substitution, 4/3 x plus 5 over 3 equals negative 17. And then we have to go ahead and simplify and solve for x. So let's go ahead and do that. Get 5x, and then here you would distribute the 7 into each one. You get positive 28 over 3x plus 35 over 3 equals negative 17. Let's go ahead and combine like terms. So in this case, we can combine this term and this term. On the side here, I'm going to say, if we're going to add 5 over 1 plus 28 over 3, you would have to multiply this 5 over 1 by 3 over 3. You get 15 over 3 plus 28 over 3, which should equal, if I'm not mistaken, 43 over 3. Yep, 43 over 3. So now we can go back here. This would be 43 over 3x plus 35 over 3 equals negative 17. Subtract the 35 over 3 on both sides. Or one thing that you could do, instead of dealing with the fractions here, what I recommend, I apologize. One thing that I was thinking of here, instead of working with fractions, we can find a LCD. And we can multiply this whole equation by the LCD to get rid of the fractions. So the LCD here would be, the least common denominator would be 3. So you can multiply this whole thing by 3 to get rid of the fractions. You get 43x plus 35 equals 3 times negative 17 is negative 51. Subtract 35, you get 43x equals negative 86. Divide by 43, you get that x equals negative 2. And there you go. In example number 12, this is just a little bit more complicated because you're dealing with the fractions in the very beginning. But one thing that is very, very helpful here is to find an LCD. At this point, multiply it to get rid of the fractions, which is what we did. And then you can solve for x after that. So we got an x value of negative 2. Once again, that isn't our final answer. You want to go ahead and plug this x value into one of the original equations that they give you. So if you wanted to, let's go ahead and choose the second equation again and plug in this x value that we got. Plug in x equals negative 2. You get that 4 times negative 2 minus 3y equals negative 5. You get negative 8 minus 3y equals negative 5. Add 8, add 8. Let me go ahead and move this over. So we add 8 to both sides, you get negative 3 equals positive 3. Divide by negative 3, divide by negative 3. You get that y is equal to negative 1. So your final answer would be the coordinate point negative 2, negative 1. And in this case, we only had one solution. All right. So once again, example number 12 is a little bit more difficult just because you're dealing with the fractions. Just be real careful when you're simplifying throughout the whole process. If you're able to, try to find an LCD, which is what we used here, to help you work with the equation more easily. And in example number 12, once again, we only got one solution. So hopefully this video was very helpful. Once again, just a real quick recap. We went over the systems of equations. And most importantly, today we looked at two different areas. The first area was solving by graphing, which is this first page, and solving by using the substitution method in this other page. So these are the first two methods of solving systems of equations. And for homework, here's what I want you to go ahead and do. So after watching this video and completing all of the in-class worksheet homework problems, and after completing the in-class worksheet problems that we looked at, here's what I want you to do for homework. So for homework, I want you to complete the homework section of this packet. This will be due on Wednesday, October 19th, when I see you all. So here is the homework assignment, which is attached to the in-class worksheet. I'm going to want you to complete example 1 through example 6. So all of this page and example 7 through 14. So all of this page as well. So these two pages will be assigned for homework. And I will check them the next time I see you all on a Wednesday. And just once again, another reminder, I do have another Delta Math assignment for you all that will be due on Friday by the end of the school day. That will be going over factoring by grouping and what we have been talking about today, solving systems of equations. All right. So if you have any questions at any point, please feel free to reach out to me. I'm here to help you all out. Hopefully this video was very helpful. And once again, please make sure that you complete the homework assignments that are listed. Have a great rest of your day.